And by learning about various design philosophies, we learned about limit states method, wherein we define what limit state is. Then how do we categorize limit states as limit states of strength, limit states of serviceability. Then we also looked at a very important concept of what characteristic strength is and characteristic loads are. And then we looked at partial safety factors, which sort of help us to convert a characteristic load into a design load and a characteristic strength into a design strength. And we sort of looked at what really we are trying to achieve by using all these factors. So I'm sure that you are going to have questions on this. So if you've had a chance to go back to the presentation, look at it, and have any questions, please go ahead.
Hello.
Yeah.
Can you please re-explain what lower bound strength and upper bound demand means? Like that graph where you explained it, that slide of the orange and the blue graph. Can you please re-explain that slide? That one
This one?
particular slide. The one with the orange. Yeah, this one.
Okay. Okay. So we are talking about safety, which means we are talking about the probability of failure being acceptably low. We can design a structure that is 99.9% safe, but it will come at a cost. We can design a structure that is 100% safe, but it will come at a cost. So we have to think of economy as well when we are trying to design a safe structure. Therefore, we are sort of trying to figure out what is the acceptable probability of failure. Okay. For that, we defined what is characteristic strength. So characteristic strength is 95 percentile strength, meaning that only 5% of the test results are likely to fall below this value. So we are looking at a lower bound of the strength. Okay.
Right.
Then, is there a question?
No. Please continue. Please continue.
Yeah. Then we talk about characteristic load, which means here we are talking about, uh, I think I've made a small error in the last definition. So in material strength, we are talking about 5 percentile strength, meaning that only 5% results will fall below this number. When we are talking about characteristic loads, we are talking about 95 percentile strength, which means that only 5% loads are greater than this value. Okay. And then what we're trying to achieve is that our strength should be greater than our demand. So the orange graph sort of represents the load effect, and the blue graph sort of represents the resistance effect. So when your blue graph is ahead of your orange graph, it means that your structure is safe, right? But then the farther your blue graph is from orange graph, the safer the structure, but the greater it is going to cost you. So we are trying to reach a value. We are trying to reach a point wherein we say that the structure is safe, but at the same time it is economical. And if you look at the graph, if you look at the curve that is shown below, that is where we say that this is the possibility of failure when the two graphs overlap. That is when your strength is in the 5 percentile category and your load is greater than the characteristic load. So a very rare case when the material is also not performing well and the loads are also extremely high, only in that case the structure will fail. And that is the sort of probability of failure that we are talking about. So only a rare case, that's a rare case wherein the loads are very high. They are higher than, they are higher than 95 percentile loads. And the strength is lesser than 5 percentile strength. So that's a very rare case wherein the structure can fail. And this is our acceptable probability of failure. Okay, now this is all at a very conceptual level. We've not got into numbers right now. We get into numbers, we get into the actual design by looking at the concept of partial safety factors. And then we look at how we sort of deal, how we make sure that there's always a safety of margin between what is the demand and between what is the capacity. Was that enough an explanation?
Yes, it was. Thank you so much.
Okay. Any more questions?
There was
Hello.
one. Yeah, sorry.
Yeah, please go on one by one,
Uh,
please.
can you please explain the first point of the partial safety factor for loads? That was a bit confusing.
Partial safety factor for loads. This one, this slide, right?
Yeah, this slide, the
Okay.
first one.
Okay. So the way we are trying to understand this is by looking at the stress strain curve of steel. Okay. So we've said that green is the maximum stress that we can allow to be developed in the material. Any stress above green, we'll say that it has theoretically failed. Okay. Now, when we say that it has failed, it does not mean that after we reach a point green, the structure is just going to collapse. That's not how safety, or that's not how the notion of safety works. What it means is now theoretically we cannot rely on that material to take any more stress. So it has failed. Okay. So that's the ultimate capacity. Ultimate means there's nothing after that. Therefore, it is called as ultimate capacity. But we really want some safety margin because of a number of reasons. The reasons are mentioned here as to why do we have to have some safety margin. So to achieve that safety margin, what we do is we divide the ultimate capacity by a partial safety factor for material. And whatever we get after that, that is called as the design capacity, or that is called as a design resistance. That is the capacity for which you design the material. That is what is design resistance. Okay. Now coming to your question. So say we are designing your classroom for a live load of 4 kilonewton per meter square. So on a normal working day, under normal conditions, you will expect a load of 4 kilonewton per meter square in your classroom, a live load of 4 kilonewton. Because of that load, there would be certain stress in the element that is taking that load. Okay, and let us say that the stress level is denoted by the point in pink. Okay, so this is a working load, or this is a service load. But we've said that there is a lot of uncertainties when we talk about loads. And all these uncertainties are listed here. You can go through them later on. So again, we have to have certain tolerance, you know, because tomorrow, I gave you an example of wherein, the class could be occupied from, 2 people to 200 people and so on. And therefore the live load can vary a lot. So we have to have a certain, so this working load is to the best of our knowledge, what is the maximum load that is going to act. And under this load, the stress that is going to be developed in the element is denoted by the point in pink. But we need some cushion, and therefore what we do is we increase this load by multiplying it to the partial safety factor for load. When we do that, we move from a working load to a design load. And the gap between the design strength and the design load is actually the safety margin. That is how much uh, redundant strength that the element has. That is safety margin. Okay, so we looked at the safety factors as well. That the I'll go to this one. So the characteristic load, we just multiplied it by a partial safety factor, and then we got our design load. And then the characteristic strength, we divided it by a partial safety factor, and then we got a design strength. Now, all these partial safety factors are greater than 1, and therefore we multiply it by load and divide it by strength. Do you understand it better now?
Yeah, but like in the last slide, in one of the partial safety factor, it is mentioned as 0.9. Isn't that less than
Yes.
1?
Yes, I'm going to talk about it. We are going to start from here, and I'm going to talk about it. And I'm really glad that you looked at the slide and sort of had this question. Uh, was it another question?
No, that's it. Thank you.
Someone else also had a question.
Yeah, I just wanted to ask something very similar. How are these numbers derived? This is page 21 or 20, right? The partial number on this one, but there was another table about the earthquake loads and the wind loads. Yeah.
Yes,
How are these
yes.
numbers derived?
These numbers are derived on the basis of a lot of experience with the way loads you can expect loads in the structure. So this is an empirical number, and it is based on engineering judgment.
No, but for example, let's take the third point because that was or the third and fourth points actually. So let's say now, for example, do these numbers change depending on whether you're on like near a fault line or not? Because then the earthquake load depends, right? Like if you
Okay.
compare Mumbai and Uttarakhand, for example,
Mhm.
there's two different earthquake factors, right? Or two
Yeah.
seismic, very different seismic factors. So would you consider a higher number for that in one of them, or would the number change depending on, or is it that both have to survive an earthquake anyway, so that earthquake load is the same?
Okay. I understand your question. Now let us try to understand what the table means, which means, so, and then try to answer your question. Okay. So, the different loads that we can expect in a structure are, say, dead load, which is the self weight of all the members, your floor finishes, MEP, and so on. And then there's live load, then there's earthquake load or wind load. So when we are designing a structure only for gravity, which means that we are not designing it for earthquake or wind, at the time, the design load combination, that is because dead and live are going to act together, right? They're not going to act separate. So at the time, the design load combination looks like this: 1.5 dead plus 1.5 times of live load. This is a partial safety factor. We've seen that the partial safety factor for dead load is 1.5, live load is 1.5. So that's how it works. Then, if you're designing it for earthquake, okay, if you're designing it for earthquake, then the design load combination is what is given in the code. When we are designing it for earthquake, is 1.5 dead plus 1.5 earthquake or wind. Okay, before that, just let me look at another combination, which, yes, I'll look at combination number 2. So if you are designing it for gravity as well as earthquake or as well as wind, the combination would look something like this: 1.5 dead plus, 1.2 dead plus 1. So 1.2 dead plus 1.2 live plus 1.2 earthquake or wind. Now the question is, why is it that the factor has reduced from 1.5 to 1.2? Would someone want to take a quick guess?
Um, the live load will wait. I'm talking about load load.
Okay, the reason is that the possibility of an extreme dead load, an extreme live load, and an earthquake occurring at the same time is very less.
Yeah. That's what I was asking. Wait,
Right?
how is the dead load less during an earthquake? Isn't the dead load like static? I've understood
Because,
that's live load, but
okay, so the dead load is static, but we have to have certain contingency because there might be. Okay, I'll go back to the slide wherein we talk about contingencies for different reasons. So we have a partial safety factor for loads because there might be a possible deviation of the actual behavior of the structure from the analysis model itself. So you might sort of figure out that the maximum bending moment that can be occurring in this particular beam is 150 kilonewton meter. But turns out that the structure is not behaving that way for some reason, and the maximum bending moment is, say, 200 kilonewton meter. So you have to have certain contingency. And when we say partial safety factor for load, it does not mean that it is only for load. It is for all the load effects. meaning that it is for shear force that might vary, it is for bending moment, it is for twisting moment, and so on. And therefore we have these partial safety factors, and therefore when we multiply this, we don't multiply partial safety factor to moments. We just multiply it to the load. If the load, then naturally it gets multiplied to moments and shear and so on. So we might think that, okay, dead load is constant, so what? So why don't we just use one as a factor? But it's really not just because the load can vary. That can happen in case of live load. That can happen in case of a superimposed dead load. That does not happen in case, that might not happen in a case of dead load, but then the load effects, meaning that the shear force, bending moment, axial force, twisting moment might be different than what we compute using our analysis model. That is why partial safety factor for dead load. So were we? Yes. So the possibility of all these extremes occurring at the same time is less. Therefore, we reduced from 1.5 to 1.2. Okay. Then there's a third case wherein we design it for dead load and earthquake load only, or wind load only. So this is the third partial safety factor. We are not considering live load here. We're just saying that the building is might be unoccupied when this happens, and then 1.5 dead load plus 1.5 wind and earthquake. Now, there's another question that one of you put up as to there is one factor that says that this might be 0.9 as well. So when does that happen? When is that we have this 0.9 as the number? So the combination related to that is 0.9 dead plus 1.5 earthquake or wind. Okay, so see, this is our structure. This is the base. This is the lateral load. Now, one of the phenomenon that can happen because of the lateral load is that the structure might overturn. And the moment because of which a structure overturns is called as an overturning moment. Right? It's pretty straightforward. You know, just you have a bottle, you know, beside you. You just try to apply lateral load. It is going to try to overturn because of a moment that you're exerting. Now, why is there a moment? Because you're applying some load. The structure is going to develop a resistance. There's a lever arm. So there's a moment. So there's this overturning moment because of which the structure might overturn. Now, what is resisting the structure, or what is stopping the structure from overturning? The phenomenon that is, or the factor that is stopping the structure from overturning is its self-weight. So you imagine you have a water bottle that is empty. You try to apply a load at its top, it will overturn very easily. Okay. Now you fill that water with water and then you try to overturn it. You will need a larger force to overturn it, which means that the weight of that bottle, or you know, its ingredient, or whatever is in that bottle, matters, and that is sort of what resists overturning of that bottle. So similarly, the weight of this building prevents the building from overturning. Now how? So if this is the weight of the building and this is the, say this is the point of overturning, then there's this lever arm which is trying to stop it from overturning, and this moment is called as resisting moment. So we have an overturning moment which is trying to overturn the structure, and then we have a resisting moment. Okay. So this is our demand. Please listen to this carefully, because see, no one is going to ask you this in exam. But if you know this and if you understand this, and this, I believe this is not very difficult to understand. This is, you know, sort of a general knowledge. So you know, you sort of get an understanding of why do we have a very different factor here. So our overturning moment is our demand and resisting moment is our capacity. Now this is very different. Dead load has always been our demand, but now dead load is deciding how much capacity we have. And we have learned this, that never overestimate your capacity. Always underestimate the capacity. Now, since dead load is helping us to resist overturning of the structure, if we say 1.5 dead load, we are overestimating our capacity, right? And that is something that we should not do. What we should do is always underestimate the capacity. And therefore, we sort of underestimate the dead load by using a factor of 0.9. So the actual dead load is 1D and underestimated value is 0.9D. For some reasons, 10%, we just say that only 90% of the dead load is really helping us resist that moment. And for that particular combination, or for that particular type of failure, we use this combination. And that's why we have a factor of 0.9 for dead load.
So basically, here we just calculate the worst case scenario that a building is going to realistically face and then use that as the partial safety factor.
Yes.
And when I say worst case scenario, I don't mean that God intends the building to fall and there's all kinds of loads at once, but the most likely loads it will face and the worst those loads will get.
Yes. So what we do is while designing the buildings, we calculate, we sort of design the member for the worst of all this. So we put all these, we sort of use all these load combinations, and then we compute ki bhai, after these load combinations, what is the maximum moment that I'm going to get in a particular beam, or what is the maximum actual force that I'm going to get in a particular column, and then we decide that column, that beam, or that slab accordingly.
Hi, can you explain the last condition, the one with the 0.9 dead load?
What did you not particularly understand about it?
The one after the overturning moment with the diagram.
Okay. So lateral load, whether it be earthquake or it be wind, it is going to try to overturn the structure. The self-weight of the structure is resisting this overturning moment. So if I say that the self-weight is acting at the CG of the building, so this is the self-weight, and this is the point about which it might overturn. So this weight times whatever this lever arm is your resisting moment, right? So your resisting moment is a function of the self-weight of the building. Now you don't want to estimate your resisting moment. We always underestimate our resisting moment or underestimate our capacity and overestimate our loads. Okay, we're talking about capacity, underestimate your capacity. So if you say that 1.5 times dead load is resisting my overturning moment, then you might be incorrect. You may not have 1.5 times dead load that is resisting your moment. Okay, so what we do is we underestimate self-weight. We underestimate self-weight by multiplying it by a factor 0.9. So we say that only 0.9 times dead is helping us resist this overturning moment, which is fair because we underestimate strength, overestimate capacity. Sorry,
Got
we
it.
underestimate strength and overestimate demand.
Yeah. Got it. Thank you.
So now you see only 3-4 combinations here. These are very basic combinations. But when we actually design a structure, say when we actually design a very tall building, we conduct wind tunnel tests, and then there are nearly 100 combinations for which we design that structure. So we design for 100 possibilities of wind coming in, different directions at different angles, with different magnitudes and so on. So these are now we need not get into these 100 combinations, but we just need to understand why are there different combinations? Because different phenomenon can occur together with a different possibility. So the possibility of all these three occurring at the same time is less. Therefore, the factor is reduced to 1.2. Then the reason we use it 0.9 because we are talking about overturning moment, where dead load helps us. When something is helping us, let us not overestimate its help. Let us underestimate it. Therefore, we use a factor of 0.9. Okay, and that's what is very loosely presented in this table, because we really need not get into the details of it. You just need to understand what these numbers mean. Okay, that's it. What does 1.5 mean? What does 0.9 mean? And so on. Then for all the limit states of serviceability, meaning that when we are calculating deflections and so on, we always use a factor of 1. The reason is that if your structure has reached an ultimate limit state, you really don't care how much it is deflecting, because anyway the structure is not usable anymore. Serviceability is related to the use of the structure, and therefore you want actual deflection. So when I say that the live load of your classroom is 4 kilonewton per meter square, I am interested in what is the deflection for that 4 kilonewton per meter square. I'm not interested in 1.5 times 4, 6. That 6 is for ultimate limit state. That is when the structure is the member is about to fail. I don't care about the deflection when it is about to fail, because I'm not going to use it anymore. Therefore, for all limit states of serviceability, we always use a partial safety factor of 1. Now, there are rare cases of 0.8 and so on. We're not going to get into that. Just, filtering information that we need. Okay, can we move on? Take it as a yes. Now, we are going to look at, as I said before, that we are going to look at the design of steel structures first from a material point of view, and then from a member point of view. So I think we have had enough information about how steel behaves as material, what are its advantages, what are its shortcomings, So now we jump on to various type of structural steel members that we are going to deal with. And these members are classified based on how they transfer forces to other members. Okay, so the basic types are, first is tension members. Now, the name itself says that you will expect this member to carry a significant amount of tension. Another one is compression members. Examples, columns, or bracing members, and so on. The third one is beams or girders, and the last one is columns, or in more specific terms, they are called as beam columns. So these are the 4 members that we are going to study, that we are going to understand the behavior of, and we are going to learn how to design these members. Okay, or how to analyze these members. As to when the member is given, you just have to find out how much force can this particular type of member transfer. So to do so, to design any member, first you have to understand ki bhai, how does the member behave. When you're saying that this member is a tension member, fine. So tell me, how is it going to behave when I apply tension force to it, and what are the ways in which it can fail. Once I know the different ways in which it can fail, I will make sure that none of the failures occurs, or my load is such that none of these failures is going to occur. Okay, so that's going to be our approach in while studying all of these members. First, just sort of understand what tension members mean, or what compression members mean, what type of stresses will you expect in these members, then what are the commonly used sections for these members, these type of members, what are their applications, and then how do these members fail. Once we have looked at all the failure mechanisms, we will see how to tackle, or how to sort of compute the strength for each failure, each type of failure. Okay, so let us begin. First is the easiest type of member and a very efficient member, which is called as a tension member. Now, tension members are structural elements that are subject to tensile forces, which tend to elongate the member. So any force that tries to elongate the member is called as tensile force, and the member is called as tensile member. Now let us talk about which type of stress can we expect in this member. So let us say that this is a member that is subject to tensile stress T. So what type of stress will you expect here? So if I just have to draw a stress diagram, you might expect a uniform stress. I think I should draw this again. So this is the cross section that I'm drawing. The stress that this cross section will experience is a uniform stress, meaning that there is same stress in the entire cross section. Okay, and what is the value of this stress? Anybody? Or, or what is, how can we calculate the stress value? Okay, going to basics. Stress is equal to force upon area. Right? We talked about the definition of stress in the first lecture. So stress is equal to force upon area. What is the force here? The tensile force T. And what is the area here? It is the area of cross section. Now, it might be a circular section. So this is the area that we are talking about. It might be a rectangular section. So this is the area that we are talking about. So if I just divide the tensile force by area, I get what is called as a tensile stress. And the tension members carry a uniform tensile stress, which means that the stress at every point, at this point, at this point, at the center, at this point, everywhere it's same. It is T upon A. Now, since the stress is same everywhere, which means that the entire cross section is resisting, is participating, is resisting that load, which means that the entire cross section is active. And therefore, it is said that tensile members are the most, theoretically, they are the most efficient members because the entire portion of the section is participating in transferring the stress or in transmitting the load or in resisting the load. And therefore, tension members are theoretically 100% efficient. Now, why do I say theoretically? Because we have to connect them to some other members. The most common way of connecting is bolting. So when you put holes in them, obviously now there's going to be some difference. by hole डाल दिए तो कुछ ना कुछ तो change होगा. Cross section is going to be reduced and therefore it is not going to be 100% efficient practically. But tension members are closest to very efficient members. Now, common examples of tension members are trusses, the bottom chord, and then the different diagonal elements in the different chord members are tension members. Then, obviously, cable straight bridges, all these cables are tension members. In suspension bridges, the main cable as well as the deck suspenders are tension members. Then an important application is called is the bracing system. So all these, ulta V's that you see is a bracing system, meaning that whenever there's a lateral load, this member, the members on this side would be under compression, and the members on this side would be under tension, and this is a lateral resisting system of a building. So all the members which are on the left side of this particular sketch are the tension members. Then if you're suspending anything, if you're suspending your roof, if you're suspending any slab from above, all these hangers are tension members. So many examples of tension members in the structures that are commonly built. Then common cross sections. The largest, the most typical cross section is an angle member. You'll see an angle member very commonly used as a tension member, especially in trusses. Now, if an angle is not sufficient, we sort of club two angles together and form a T section. Those T sections are not easily available in the market. Therefore, we always club two angle sections to form a T section. Then there's channel section, box section, and so on. So this is the most commonly used sections. So just in case for any of your projects, you have a tension member and you want to know which type of member you could just come back to this slide and you could just select any of this. Now, sometimes a single member is not sufficient. Therefore, we club two members, which are called as compound sections. Sections like these. So here we have compounded two channels and two flat plates. Here we have compounded two channels and so on. We're not going to get into the details of it. Then we have compression members. Now, naturally, if tensile forces called tensile members cause tensile members, and compressive forces cause compressive compression members. So these are subject to direct axial forces, which tend to reduce their lengths. Now, just like tension member, these carry uniform compressive stresses under concentric axial load. Okay, so everything else remains the same except that now the nature of the force is reversed. It was tensile before, it is compressive now. But there's a problem with compressive members. That is different, or this is a problem that tension members do not have, and compression members have. Would someone like to take a quick guess as to what this problem is? Okay, then just imagine an exercise in your mind. If you have the means for doing the exercise physically, please go ahead and do it. So imagine you have a steel scale and you just hold it in your arms, both of your arms, and you try to pull it. Okay. Now, is the geometry of the member going to change?
No.
No, right? But now you hold it in your arms and you try to compress it. Is the geometry going to change?
Yep. Yeah. It'll
That
bend.
it will bend. Okay, so this phenomenon wherein the uh, the stability of a particular member is disturbed because of compressive force is called as buckling. Okay, this phenomenon is called as buckling. It is different from bending. Now I know this is some additional information, but just listen to it. So when the deflection is in the direction of force, it is called as bending. Nothing complicated, okay? Just don't, just listen to these words and, if this is a beam, so a beam bends. So the deflection is in the direction of loading. But now you took this scale in your hand and you applied a force like this. So the force in this direction and the deflection is this in this direction. So when the force and the deflection are in the same direction, it is called as bending. And when the force is in one direction and the bending is the perpendicular direction, it is called as buckling. Okay, this is buckling, this is bending. So compressive members buckle, that is a problem with them. And therefore, when we started the lecture, we were talking about why seal members, there's a problem with seal members when they're used as columns. That is because strength wise, you need a very slender section. A shorter section will do, but by stability wise, it will not work because it might buckle. Concrete does not have that problem because strength wise itself, you need a large section and that section might not buckle at all. So that's the problem with compression members, which we are going to discuss at length when we study compression members. But now just to give you a head start. So the member strength is a function of cross-section shape. Now again, I would go back to the first lecture wherein we discussed about two parameters. One is modulus of elasticity, which is Z, and another one is radius of gyration. And I told you that modulus of elasticity is a measure of bending strength and radius of gyration is a measure of buckling strength. So the member strength of compression members is a function of the radius of gyration. We are going to learn further that not only is a function of radius of gyration, but it's also a function of length and end support conditions, material, and so on. Okay, we'll get to this later. This is just an introduction that I just know that this is a function of this. Now, since it is a function of radius of gyration, we looked at examples wherein we said that if the material is distributed far away from a particular axis, larger is going to be the radius of gyration. And therefore, in a compression member, the area is spread out as much as practical. Okay, and therefore a hollow circular section is the most efficient compression member because all of its, all of the material is at a maximum distance possible from the centroidal axis. And therefore, the radius of gyration is maximum for a hollow circular section. And therefore, it is the most efficient compression member. Okay. So examples of compression members are chord members in trusses. Now, the top chord is a compression member, and other chords, which some of them are tension members, some of them are compression members. Then the bracing strut. I told you that whenever there's a lateral load, if there's a lateral load from the left side, all these elements are going to be under compression and all these elements are going to be under tension. So bracing strut is a compression member and a tension member as well. It depends upon where you are applying the force from. Then interior columns in buildings. And finally, bridge piers. So bridge, you can expect by compression members, I host me. There's nothing surprising about that. Now, why do I say interior columns of building? Now, if say this is our building, have we discussed this before?
No.
Okay. So just imagine that these are your columns. So this is your central column. So your span in all the directions is same, and therefore you will expect this column to be predominantly subjected to axial force only. Okay. Because there is no unbalanced span, there is no different span, because of which there is no unbalanced moment. And therefore, you can expect this to be a compression member. Okay, but let us talk about this particular column, the column here. In this column, you have a span here, but you do not have a span here, because of which there is going to be a bending moment. If this is the column and there's only a slab here, naturally the slab is going to try to bend this column. So this column is not a compression member. This is a beam column, meaning that it has a compressive force along with bending moment. Therefore, this is called as a beam column. Now let us talk about this column here. That here this sheet is done. So you have a column here, and there is a slab on this side. There's a slab on this side. In both the directions, the slab is discontinuous. Therefore, the slab is trying to bend this column like this, and it is trying to bend the column like this. So this is again a beam column because there's significant amount of axial force and there's significant amount of bending. So it is a beam as well as it is a column. So these members are called as beam columns. And therefore, in my example, I say interior columns of buildings because an interior column might be subjected to lesser bending moment as compared to the columns at the periphery. And therefore, this is an example of compression member. This is not. Okay. So for this type of column where there is bending only about one axis, this is called as a beam column with axial force and uniaxial bending. There's bending only about one axis. But if you talk about this column, there's bending about this axis and there's bending about this axis as well. Therefore, this is called as a column with axial force and biaxial bending. Uniaxial, biaxial, simple. So these are our compression members, and these are typical cross sections for compression members. Now, in most of this, you will see that it is tried that the area is as far away from the axis as possible to maximize the radius of gyration. And as we established, pipe or the round tube is the most efficient compression member for a given area. Okay. Then we move on to the third type of members, which is called as beams or girders. So beams are subject to transverse loading. Such a type of loading is called as transverse loading, and they resist these loads by bending and shear. Very basics. So primarily they carry bending stresses which are maximum at the extreme fibers. Now perhaps I think here you might need some revision because I don't want to start with an assumption that you know this and then move on to further details without you understanding this. So we talked about a compression member and the type of stress that you might experience in a compression member. Now, if we talk about a beam, let us say this is a beam, and there's a UDL on this beam, because there are support conditions here. Now, I want to know that because of this transverse loading, what is the type of stress that is developed in this material? Here it was straightforward, tension member, direct stress, which is uniform throughout the section. But it is not the case here. So if I sort of take a section here, so this is my section. So firstly, I have to understand the nature of the force. If it is say it's a homogeneous material, say if it's only steel, this is a block of steel or block of wood or block of concrete, then this is something that you already know, we are just revising. The section which is above this will be experiencing which type of force?
Compression.
Compression, right? The material or the section which is below this line will experience tension, right? How difficult is that? It is going to bend like this. Okay, here there's elongation, here there's contraction. Okay, since there's contraction, this is a compressive force. Since there's elongation, this is tensile force. Now, can someone tell me what is this line called?
Neutral axis.
Neutral axis. It is neutral. Irrespective of what load you put, it is not going to budge, it is not going to be stressed, it is not going to be strained. It is called as neutral axis. Okay. So the section above neutral axis is under compression, below neutral axis is under tension. Now the question is, how much compression, how much tension? Is it that there is going to be a uniform compressive force here? Yes or no?
No, the most compression will be at the top and the least at the towards the center.
Right. So the stress that varies in this cross section looks something like this. So the compression is maximum here. So this is the maximum compressive stress at the top, maximum compressive stress at the maximum tensile stress at the bottom. And then the stress varies from 0 to a maximum value. Okay, this comes from understanding of bending, for which I'm sure you have studied bending, what bending is, how to derive this. I'm sure you have looked at this equation. E upon R is equal to M upon I is equal to F upon Y. Sometime, some long back, 30, 40 years back, you might have looked at this equation. Okay, this is nothing but that equation. And this just means that the strain varies linearly up to failure and all. Not gonna get into that. But my point is, when we are talking about tensile members, the stress is uniform. But when you're talking about a beam, the stress is maximum at the extreme fibers, and all these fibers are stressed so less. And therefore, beam is not a very efficient structural member. Because the material in this zone, you are not utilizing it completely. Okay, we just say that this, whenever the stress reaches a maximum value, why beam has failed. And therefore, most of the material in a beam is not mobilized or not utilized properly. And therefore, beam is not a very efficient member in terms of material use. That is something that you have to keep at the back of your mind. So majority of the material remains unstressed in flexure. Now there's one more thing to it. Now, when I talk about a tension member, say this is a tension member. So the tensile force at point 1, at point 2, at point 3, at point 4 is going to remain the same, and that force is T. But if I talk about a beam, the moment at point 1, moment at point 2, moment at point 3, moment at point 4 is going to be different. Why? Because the moment varies along the length. Now, if I have to draw the bending moment diagram for this particular case, it will look something like this. So at 1, it is 0. At 4, it is 0. At 2, it is WL square by 8. Quick refresher. And at 3, there is something in between. So does it mean that I design a different section here? I design a different section here, a different section here? No, because practically it would make no sense. So what do? I just select the maximum moment and I just provide the same section throughout the length. So imagine you are designing a beam for a maximum moment only at one location. And even in that, you are designing it only for the maximum stress. Bhai ye stress aa gaya, to beam fail ho gaya. So beam is that inefficient a member because along this length, the stress is going to be further less. Just get a crux of what I'm trying to say. The moment is maximum only at one location. You select a section for that location and you provide it everywhere. And therefore, beam is not a very efficient member. Any questions?
Can you repeat the last part again?
Okay. So, how do we design a beam? Now, why do we need these bending moment diagrams? Why do we need favors diagrams? Because we have to understand what is the maximum value of bending moment and where does it occur. Okay. So in this case of a simply supported beam, it will occur at the center of the beam and the value is W square by 8. The value here might be different, say W square by 12. The value here might be different, say W square by 24. Here it is 0. So does it mean that I will give different sections along the length of the beam? Meaning that, will my beam physically look something like this? And if I say draw cross section here, it is a rectangle. But then if I draw a cross section here, it is something like this. So will I have tapered sections? I can, but practically I won't, because that does not make any sense in terms of ease of construction and then production of that particular section and so on. So what do? We provide whatever is required at the center. So whatever depth is required here, we will provide the same depth throughout. But जरूरत है क्या? जरूरत नहीं है, but we are providing because of practical reasons. So in along the length, we are providing a depth that is for a lot of length, we are providing a depth that is not even required. But we do it because that is the depth required for a maximum demand, and that is practical. That works practically. Further to that, now that's at a member level. At the section level, you see that the stress is maximum only at the extreme fibers. Beach mein, the stress is less, right? So stress less hai, so why do you want to put more material there? Or whatever material has been put in this portion is going to have a small stress, right? So what does that mean? It means that you're not utilizing the materials fully. If the material can take 250 megapascal of stress, the stress here will be somewhere around 50, 60 megapascals. So meaning that you're not utilizing the material, you're not giving it a chance to take stress. And therefore, in terms of material use, beams are not very efficient members. Is it clear?
Yeah.
So now, what does this diagram say? This diagram says that if I use the rectangle section here, I might use this portion very efficiently. I might use this portion very efficiently, but this portion I might not. So what do? I use an I section. Now, if I'm using an I section, anyway, here the stress is going to be less. So this material is enough to take care of that. Here I'm providing larger material because there's larger stress. Here I'm providing larger material because there's larger stress. And that is the reason why I sections are most commonly used beam sections. Because they sort of get us what we need. We need material efficiency. Agar stress extreme fibers mein zyada hai, if the stress is maximum here, so I'll provide maximum material here. Here I'll provide minimum material. And that is the reason why I sections are the most commonly used cross sections. Or if it's any other, if you're using a compound section as well, you'll make sure that maximum material is towards the end. Okay, we'll get into the details later on. Abhi sirf basic samajh lo. And the last one is beam column. So column subjected to significant bending in addition to actual load is called as a beam column. We saw the example of edge column and corner column. So we're not going to get into the details of it. Bending will be uniaxial or biaxial. We looked at this. With here, I believe we have enough basic information to start with this course. So any questions here?
Is the neutral axis a point or a axis that actually exists in a beam, or is it just something we use to theoretically understand the compression and tension?
Okay. So if I draw elevation of a beam, these are the supports. This is the loading. After it bends, you're going to have maximum compression here, you're going to have maximum tension here, and then there'll be one axis along the length wherein you will have neither compression nor tension. And this is nothing but the neutral axis. If I draw cross section, this is your neutral axis. Okay, so this is your neutral axis in cross section, and this is your neutral axis in the longitudinal section. So it's a kind of a plane. We try to visualize it. It's a plane, which in cross section looks like this. In longitudinal section, it looks like this. Now, I'm not good at 3D drawings, but I'll just try to make one. So if this is your beam, so you will have your neutral axis something like this. So in cross section, you will see this, and longitudinal section, you will see this. Do I
So
answer your
there
question?
is physically a plane that does not actually undergo any compression or tension, right? It's not
Yes.
just a theoretical plane.
No, so that's a theoretical plane, but uh, so that's a theoretical plane because we are talking about a plane wherein in the entire length there is going to be no stress. But practically, the forces are not as ideal as we want them to be, right? So practically, your plane might look something like this.
Because concrete is fully homogeneous, the plane will be more uneven in concrete than, let's say, steel, which still will have a slightly less uneven plane.
Yes, yes. So it is a theoretical axis, it's a theoretical plane, but practically also there's going to be an axis that will never have any stress. That will not have a stress under that particular loading. That's called neutral axis.
Thank you.
Yeah. Any more questions?
Yeah, I had a doubt.
Yeah, please.
When we were talking about how different type of forces are acting on a column, if it's a center column or edge column or a corner column, then
Yeah.
do the formation or the placing of steel changes accordingly?
Uh, it doesn't, because normally in columns always provide steel along all the faces. Okay, so if it's a central column, there is a chance that the steel in all the faces might be uniform. Okay, just to give you a disclaimer, this is, just this is just to give you an idea. That is not really what practically happens. This is just to give you an idea. There are हजार factors which decide ki reinforcement how to give, कहाँ पे कितना डालना है. That's a different story. Okay, but this is just to give you an understanding. Say if it's a central column, the first case is central column, then you might have the same reinforcement. You might have the same reinforcement along all the sides. Let us take a second case wherein it is our edge column here. So if this is my slab, say it is an edge column here. So it might happen that you will have a larger reinforcement on this face and a smaller on this one, and then again a larger on this face. So there's a smaller reinforcement on this face and there's a larger reinforcement on this face because your bending is going to be like this. So these bars are going to be under tension. And similarly, if we take, say, a column here, then it might happen that here you will have larger reinforcement. And here you'll have smaller reinforcement. Because it bends this column like this, therefore this will be under tension. This is tension, this is compression. So this will be under tension. So yeah, it may vary, but there are हजार factors.
Okay, thank you.
Yeah. Any more questions? No questions? Perfect. Then I have a set of questions for you, and that set is called as quiz 2. So I'll give you a couple of minutes, get your calculators, pen, paper, and we'll do a small quiz again based on what we saw in the last lecture and this lecture. Okay. So you might say that what is taught today is taught today. So how can we answer questions like these? I've asked very simple questions. So even if you've paid attention in the lecture, you won't need to think twice about it. Okay. And I'll take the time factor in consideration and give you enough time to think about these questions. Let us see, how you do after that. So it's 11:59. Take a couple of minutes and let me know whenever you're ready.
Is it possible for you to take the test next time so that we go through the notes as well? Whatever we learned today and last time.
So there are not many questions from what we learned today. The majority of this test is based on what we learned in the last lecture. Only a few questions, that too very general. So I believe there's no, really no, what I can say, prerequisite that you have to go through today's presentation to sort of give that test. And plus, okay, I give you this. What we can do is if there's any question that is related to what we learned today and you're stuck on it, we can discuss it, and after you can answer your own question. Does that work?
Okay.
Okay. So shall we start?
Yeah.
Okay, perfect.
How long do we have for it?
20 minutes.
Thanks.
If you are stuck anywhere, we can discuss. So I'll close the test at 12:20.